That means when you have a loading like this, experimentally, what is the angle or angular deflection at your support? This value is experimentally determined. Okay. Now, of course, as a structural engineer, we must ask ourselves this question all the time. It's easier for us to assume a hinge support, a fixed support, or a roller support. We can always do that. Mathematically, that gives us great pleasure and great advantage in arriving the mathematically meaningful result. But in reality, you must ask yourself these questions. How realistic is your assumption versus the actual design? Now, you must know that some of you probably have seen that from your work. You probably already know that there's no such thing as called rigid support. There's no such thing as called hinge support or perfect hinge. There's always friction. Friction is everywhere, right? And there's, of course, no such thing as called perfect roller support. Maybe something similar or close to it, but no such thing as a perfect roller, perfect hinge, or perfect fixed-ended. No such thing. Everything is always and can be measured or characterized by a spring constant. That's the reality we structural engineers must embrace. All right, let's come back to here. Okay, let me try another example. So this is the case to show this effect. And let me try another example. This is example 6. Now, in this example, we're going to consider not just a single degree of freedom system. We're going to consider is multiple degree of freedom system. So we're going to consider this kind of structure. It's a 3-bar 2-spring system. It's also a spring bar system, but it just gets more interesting rather than the spring bar that we have seen in example 4 and example 5. Now we're going to consider this. Suppose you have a bar member like this, and it is connected to another bar member like that, and also another one like this with a hinge, or you may call it a roller. I don't know whichever is easier to explain this. However, to make sure that the structure is stable, we have to introduce rotational spring at this point. Of course, before we do that, so let's define this point. So let's call this A, this is also point B, C, and D. So at points B and C, there must be rotational springs. Otherwise, the structure is not going to be stable, as you should know. That means we're going to introduce rotational spring here, rotational spring here. And the geometry of this column is going to be like this. So we're going to say that this L, it's capital L like this. And where's the force? The force is applied at this end. Because this structure is subjected to an axial force P. That's what we call this a column member or a column. Now, if there is a force P here, you will induce a reaction force P here. That's reaction. Now, what we need to know is to determine the buckling load. So that's the problem. What we need to do is to find out the PCR, the buckling load of this structure. And of course, by assuming that the regular E and I's, they still apply to this structure. So you have the E and I's. It's uniform. They don't change. Now, so how do we solve this problem? First, if we use the force approach, then we're going to use the free body diagram. So the first thing to do is to consider a free body diagram with a type of deflection profile. And that means if we draw the column like this, and the first deformation profile we're going to consider is something like this. And we're going to consider that upon the loading of this axial force P, this member is going to deflect like this. That's from A to B. And that means from here, you're going to have the first rotational angle. We call this θ1, right? We can certainly do that. And in the meantime, we also will, of course, we also accept the reality that there's going to be another rotation because at points B and C, they are both springs. That means they can rotate. And that means at the other end, there's going to be another rotation, which is something like this. Of course, I did not, they should be the same if I don't make them identical. But they should be, the length should be L. And this angle here, we're going to call it θ2 because we're not sure that this angle θ2 will be identical to the other angle θ1. In our formulation, we will not assume that these two will be the same. So that's why we formulate this way. If one is θ1 and θ2, of course, by this kind of definition or schematic illustration, you understand that I'm making θ1 greater than θ2, right? Of course, it could be the other way around, but the point is not to make θ1 to be identical to θ2. If that's the case, there's going to be another angle right here, like this. And that means I'll draw another line like this.
Hello.
Yes.
Professor, there is one of the students. He's waiting for you to get him in.
Thank you. Just saw him. Now we're going to show this kind of schematic. So to help you better understand or determine the angles, it is advantageous to draw two horizontal lines at both point B and point C. Now, if at point B, see, this A and this D. If this angle is θ1, of course, we know that this angle is also θ1, correct? That we know from geometry, right? And if this angle is θ2, and that means this angle here must be also θ2, correct? Right? It must be. Now, what is the angle here? There's also another angle, which is from here to here. You know that it's not going to be 0. So what is this angle? This angle is going to be θ1 minus θ2. So that's this angle. Now, when we are taking the force equilibrium, we have to know that the amount of internal moments acting on both members. So by looking at the first member, and this is page 16, we're going to add another one. That will be 17. So in step 2, we consider member AB. And member AB is like this. And we want to know that what forces we have acting on this member AB. So here we have A here, B here, and we know the angle is θ1, right? That we know. Now, At point A, there's no bending moment, so we know that there's a moment at point A. But at point B, because there's rotational spring, so there is an internal moment, right? Just imagine this. Before the deflection, this is our structure. You have a rotational moment like this. If you do not bend it, there's no internal moment. In this KS will produce no moment. But what if I bend it? What if I bend this number like this with an angle theta? So what is the amount of internal moment acting on these two members? And from here, we know that the internal moment must be acting in the direction against the motion, which means there's going to be internal moment acting like this. And this moment equals to spring constant Ks times the angle of rotation, which is theta. Would you agree? Right? So coming back to the this one here. In this problem, in this case, you need to know that what is the actual deflection applied to member AB. So the way to determine this is by using this. You draw member here and you just extend it like this. And we know that the next member we have here is actually bended at a slightly different angle. And this angle is theta 1 minus theta 2. And right here, this is theta 1. But the actual amount of rotation is what? Is not theta 1 or minus theta 2. The actual amount of rotation is actually from here to here. Would you agree? For member AB. Would you agree? Therefore, here, what is this actual amount of rotation? The actual amount of rotation is actually the summation of theta 1 plus theta 1 minus theta 2. That's the total amount of rotation. How do we know that? It just by making this reference line horizontal like this. Because this part is theta 1 minus theta 2. And this part is theta 1. So the total angle here is just theta 1 minus theta 2 plus theta 1. And that is going to be the angular internal moment, which is going like this. This is the internal moment.